Hi guys. So in this lesson, we'll be studying about an idea called ionization energy, which is basically going to help us understand and prove the basic electron arrangement in atoms. How the electrons are arranged in shells. How can we prove that? Well, we prove that using the idea of ionization energies. And what is that? Well, the basic idea is that one way to prove the fact that electrons are in different shells and not the same shell is that we're going to try to remove electrons from the influence of the nucleus. And the electrons will require some energy, and the energy they required, we will study that. Now, some electrons will be lost easier than others. First of all electrons are attracted towards the center because they are being pulled by the nucleus. But the electrons that are closer to the nucleus will be pulled more strongly, and the electrons that are further away will be pulled less strongly. And what we're going to do is we're going to start removing electrons from atoms and study the energy it requires to remove a certain electron. Now, so obviously when you take a neutral atom and you remove an electron from it, you are left with a positive ion, because that's what happens. So if I take an element X, in the gaseous state, it'll be easier while later explain that. But if I remove 1 mole of electrons from X, or even from one atom, I remove 1 electron, I get a 1 plus ion. I can write this equation like this, or I can write the equation like this. In both cases, they are the same equation. And this, by the way, these are chemical changes. The idea that there is a certain amount of energy required to remove 1 electron from an atom. And this energy is called ionization energy. More specifically, when you take a neutral atom and make it lose 1 electron, it's called first ionization energy. And what we're going to do is we're going to study ionization energies and first ionization energies of various elements. Now, it could be that you might think that, well, cations lose, metals lose electrons to become cations, and sodium is a good example of that. So sodium can lose 1 electron and become a positive ion. Now this is basically the writing of the equation that represents the first ionization energy of sodium. And this actually has an enthalpy change. The enthalpy change for this reaction, which is the energy change, happens to be about 494 kilojoules per mole. That means for every 1 mole of sodium, gaseous atom that becomes gaseous ions, 494 joules of energy are required. That means that's the electron being removed in sodium. Now, we look at the more detail of atoms and we look at other atoms, but just first honing into this definition of first ionization energy. So if I write the first equation that represents the first ionization energy of oxygen, it can also apply to nonmetals. I can have nonmetals lose 1 electron and they can become positive ions. They might not naturally become it, but they can. Now, clearly, if you notice, the value for this is much greater than the value for sodium's ionization, and which can give you an idea that this is probably why sodium does become 1 plus ion but oxygen doesn't. From your O-level studies, you know that metals become cations and non-metals become anions. And the reason for that is non-metals losing electrons require much more energy than metals. Or you could say that metals' ionization energies are lower than non-metals. But that we'll discuss later, how the variation of ionization energies occurs between elements. Today, this lesson is about understanding the idea of ionization energy, understanding the attraction electrons feel from the nucleus, also understanding the energy required to remove such electrons. And that's something that you need to understand, that there are electrons are repelling each other but are being attracted by the nucleus, and there is energy required to remove that electron. That energy required is called ionization energy, and we can lose 1 electron from 1 atom. That's called first ionization energy. We can lose more than 1 also, but initially we're going to be talking about the first one. Like, this is the equation that represents the first ionization energy of sodium and the first ionization energy of oxygen. Generally speaking, from an atom, the outermost electron is the most likely to be removed because it's the furthest away, so it's the easiest to be lost. So be it sodium. Now in sodium's configuration, if you remember, sodium's configuration in the basic shell terms is 281, which means that it's the one electron in the outermost shell that is being removed. Oxygen's is 2,6, which means that when I'm losing one electron from oxygen, it's one of these 6 electrons that are being removed. And obviously sodium becomes 2,8 and oxygen becomes 2,5 after having lost one electron. Now we can look at some more examples of other elements and their ionization energies. First, ionization energies first. Here is lithium. The lithium atom in the gaseous state is losing one electron to become a lithium gaseous ion. And it's always the valence electrons that are being lost. If you remember, lithium's configuration was 2, 1. So it's the outermost electron that is lost. The same applies to some other elements. And what you will start realizing is that, like I was saying earlier, that if you notice, this ionization energy is not that high. It's about 500, which isn't that high.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
But other elements like here are oxygen's first ionization energy equation, sulfur's first ionization energy equation, copper's first ionization energy equation. And you can see the values differ from element to element. You will notice that it's the metals that will tend to have low ionization energies and the non-metals will tend to have high ionization energies. Oxygen in the 1300s, sulfur 1000. But if you remember, sodium was less than 500. And the way we define it for now, that the fact that the equation for the first ionization energy, or short formed first IE, for any element is when 1 mole of the gaseous atoms of the element lose 1 mole of electrons to become 1 mole of positive ions. Yeah, and the enthalpy change in that such a reaction is going to be first ionization energy, and it will always be endothermic, guys. Why? Because energy will be required to overcome the force of attraction. Remember, all ionization energy values are positive. They're always going to be positive. Why? Because they are going to require energy. And I'll scroll up to the earlier part. If you notice, if I look at a cell like this, even lithium, is that each electron in lithium is being pulled by the nucleus. Yes, the electrons also repel each other. You know, they do. But the attraction is greater than the repulsion. So when I'm going to lose this electron for lithium, I'm going to provide energy. Hence, first ionization energies are going to be endothermic. All ionization energy values are going to be positive. They're going to be endothermic because you're going to require energy to overcome the attractive power of the nucleus. Therefore, work needs to be done to overcome the attraction between the negatively charged ion and the positively charged nucleus. Okay, and what you will be tested on is that one of the most basic things they ask for is to be able to write the equation for the first ionization energy for any element. So if I were to write a couple of more, what would be the first ionization energy for let's say iron? Fe, gas, again gaseous atoms. All gaseous atoms become Fe, 1 plus gas plus E. Then it could also be for a non-metal, fluorine, which is a non-metal halogen. It tends to want to gain electrons, but I can make it also lose it. Now, I know from experience that this ionization energy is much more endothermic than iron's. I can even make argon, the noble gas, lose electrons, and that's okay. It is physically possible. It will require the most amount of energy because understanding that it's already a stable configuration, 288, you're disturbing a stable configuration, you'll require much more energy. Iron is 27, sorry, Fe is 27, it'll become 26. Okay, and we will not worry about writing the electronic configuration of transition elements. We'll do that later as part of this chapter, but not right now. All right. Okay. One last thing. What about nitrogen? It's got 7 electrons, 5 in the outermost shell. Nitrogen, just to give another example, this equation will represent the first ionization energy of nitrogen. And all of these are going to be endothermic. Nitrogen's is about 1400 kilojoules per mole. If you remember, oxygen's was about 1300. Fluorine's is going to be about 1500, 1600. I don't know about the exact value, but they do exist. Let me find them and actually just give them to you, just so that you don't have to learn these values ever. You don't have to learn them. You have to understand why they differ, and that part we'll do later. But this lesson was just about introducing you to the idea of ionization energy. It is the energy required to lose the outermost electron. For some elements, the energy is very high. For some elements, the energy is very low. For example, iron's energy, because it's a metal, is, we find it to be pretty low. Lower than, if you notice, for nitrogens. For fluorine, it's pretty high. It's about 1700. It's 1680 kilojoules per mole. All right. Argon's is going to be even higher. It's going to be, argon's is, argon's pretty high too, 1520. All right. Neon's is 2000, So these non-metals and noble gases have very high ionization energies, while the metals have lower first ionization energies. But anyways, so you will see sometimes there are some that have first ionization energies reaching up to 2000. Helium's is, by the way, is the highest first ionization energy. And that, I should tell you, helium, the noble gas, that can also become a plus ion. It has the highest first ionization energy. It requires the most amount of energy to make helium react, lose an electron, which can also tell you that helium most likely is the most unreactive element in the world. All right, because to making it, its electron is so tightly held, it requires so much energy. And you can even understand why its electron is so tightly held, because it has only one shell, so it must be close to the nucleus. The other guys are having multiple shells. The outermost electron is further away from the nucleus. But that's one way to study the electron structure of atoms, just by looking at first ionization energies. We can also look at successive ionization energies, meaning making an atom lose all of its electrons. But that I'm going to put in the next video lesson. This video lesson is literally all about introducing you to the idea of ionization energy, which is the work done in removing an electron from an atom. The first electron to be removed from an atom is always the outermost, the one that's most loosely held. And you should be able to write the equations of any element and their first ionization energy, or the equation that represents their first ionization energy. Then in the next video lesson, we're going to be discussing about how successive ionization energies can help us determine the electron structure of atoms. Ciao. Hey there. If you found this A-level chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?